Welcome to our wind project, including the modeling software Retscreen. Here's our content list. First, we talk about the introduction and the location choice. Secondly, is the modeling part with Retscreen. And third, we talk about the financial analysis of the modeling part. And last but not least, our conclusion to the project. And first, we must find a location for our wind power plant. We have a lot of ideas where the location is, but we choose New Zealand because we find many articles about the good wind resources there, especially mentioning the high average wind speeds. And currently, 60% of the electricity in New Zealand comes from wind in the year 2021, and the numbers of wind farms is increasing constantly there. They want they want to have in the year 2035 over 20% of the electricity comes from the wind. And the government benefits this development. They want to have in the year 2025 over 90% of the energy supply shall be comes from the renewable energies, including the wind. And so they make benefits for the wind energy industry with falling wind costs around 10% for offshore wind turbines in this time. And yeah, the sentence on the left bottom shows the situation, the wind situation, very good in New Zealand, and the situation how people think about the wind resources. They say that the least windy location in New Zealand has a better wind energy potential than the windiest location in Australia, which is located next to New Zealand. And where's New Zealand located? New Zealand is located in the South Pacific, in the east of Australia, and belongs to the continent Australia and Oceania. And you see in the right picture, New Zealand is an island, which maybe is the reason why they have got good wind resources. And our goal is now to find a location that is close to the sea, which produces the energy, and is close to the city, which I use this energy directly. And you see our selected area is located on the North Island in the South End. And there's the capital of New Zealand, located. It's Wellington, and the city has about 200,000 inhabitants. And our selected area is in the west of Purio City, which is a part of Wellington. You see it on the right picture. The area is located on the southern hemisphere at latitude 41 degree and in the eastern hemisphere at longitude 174 degree. And you see it on the left picture. There are only little population is living there, and in the distance over 1,000 meter to the power plant location, you see it named Colonial Knop. There is the first building that is a farmer region, and the area is farmer region because there are many open spaces which are used for agriculture things like the pastures for sheep and so on. And you see it on the right picture. There's a street through the area, which could use for the transporting the material to the power plant, and which could use for the connecting the generated electricity to the power grid of the city. Yeah, but what are the exact wind conditions now in this area? To answer these questions, we use the Global Wind Atlas. And first, we make some settings about the area and the height. And the area size, you see it on the left picture, is 4 square kilometers big and has a length and width of 2 kilometers. On the right picture, you see we choose a height of 100 meter. Now, come to the conditions for the wind power plant. And first, we talk about the important condition, the wind speed and the wind direction. And you see it in the graph at the right bottom. The wind speed varies between 10.5 meter per second to 12 meter per second. And you see it in the left picture, it's a lot of purple and red color, so it's very good there. The wind speed of the 10% windiest area is 11.70 2 meter per second, which are used in the modeling part with Retscreen. And you see in the two wind speed roses on the right side, they show that the wind comes from the north and northwest. So 60 to 65% comes from the coastline, which is also good to know. Secondly, talk about the power density. You see it in the graph that the power density in the area between varies between 1100 watt per square meter to 1700 watt per square meter, which is also shows very good condition for wind energy. And yeah, the power density for the 10% windiest area in the selected region is 1547 watt per square meter, which is the value we used in the modeling part. Then last, talk about the roughness factor in this area. The roughness means the roughness length of the terrain surface. And the roughness varies between 0.03 meter, you see it on the left picture, to 0.3 meter. And yeah, the roughness could influence by forests and buildings, but as I show you the location on Google Maps, there are many fields and only a little forest and no buildings in the area, which could slow down the wind. But all in all, you can say it's a very good area to produce wind. Yeah, and here in the table is an overview over the conditions for the wind power plant we figured out by Global Wind Atlas. We are now used for the next step, the modeling part with Retscreen.
Hi, I'm Patricia, and I have done the first part of modeling with a red screen. The first thing we have to do is to configure the program in setting and put the preferred language, in this case is English, and a currency, which in this case we have put the dollar. Um, The choice location has been Wellington in New Zealand for various reasons, which Tim has already explained above. And we have to select two type of power plants. The type of power plants we want, which is one turbine, and the power we want, in this case, for example, we have put about 100 kilovolts. We also specific well the coordinate of the sheet choose to place the plant. One of the most important things to know for the construction on of wind farms is the wind speed. When specific the above data, we get a graph on this of the with speed that there are throughout a year in New Zealand. It is you can see that it is more or less constant in the time in a month, being slightly higher in the month of July, but doesn't matter very much. It is estimated that the average wind speed per year is 5.2 meter per second. We want to see the cost of the kilowatt. So we are going to make an estimation and provide information to the program for our plan. With this, we have found out that the price will be around 2.278 dollars for a kilowatt. The program gives us several wind turbine options, so we are going to select only the speed for our location or 18 in 18 meters. We also rounding the capacity factor to 28% until the megawatt we want to get to about 18 megawatts. Doing this, you can see that the electricity export revenue is around $50,000. In addition, we can see the emission of our plants. by looking at the gross annual GNG emission reduced of 93% with losses of 7%. The next step in the program is to find out with the global with exponent. The speed is 100 meters, which is 11.72. We also verify that the spawning width share in 0.14 and falls within the proposed range. Um, for our turbine, we have to set the condition. We choose the 19-meter turbine from the company Vestas and to provide us with a quantity of 81 megabytes, around 81 megabytes. We will need to put about 27 wind turbine. Finally, the most important in the power plant is the power that we go to get. We can now move on this final part, we need to see the power that it will provide us. First, we have to comprove the temperature and the pressure level are correct for our locations. We can see that there is an adjusted energy production that is approximately 18, but doesn't matter very much. And in the graph, we can choose our speed that is 11 78 for 100 meters. And in the graph get us the information that for concluding that it will give us about 15 kilowatts per hours.
I'm Huang Huanchen. Let's start the financial analysis part. The New Zealand Wind Energy Association's 2023 Legend LCA study reports capital costs for onshore wind at 2,719 euros per kilowatt per hour with total project costs of around 142.29 million euros. Based on the Retscreen guidelines, we allocate 3%, 3 million euros for feasibility study, 6%, 9 million euros for development and engineering, and 30%, 100 million euros for the total cost for the power systems. Miscellaneous and balance of system costs are estimated at 10 million euros, while the contingency plan includes a 5% contingency, 6.55 million euros, and 8% interest during the construction period. Annual costs include 3.1 million euros in operation and maintenance, with fixed O&M cost totaling 1.22 million euros, bringing total annual costs to 4.32 million euros. Major components replacement every 10 years are estimated at 1 million euros. For the financial analysis, we used a 7.7% discount rate, a 9% reinvestment rate, and a 20 years project life. The quality investment is 57.22 million euros, and the annual revenue from electricity exports is 17.33 million euros, and the export rate is 0.08 per kilowatt per hour. The project is financially viable with a pre-tax internal rate of return of 9.2% and a net present value of 9.23 million euros. The project has a simple payback period of 11 years and a return on equity of 12 years. The benefit cost ratio is 1.2, indicating that the benefit outweighs the costs and the debt and the debt service coverage ratio is 1.3, meaning that the project can easily pay off its debt. The cash flow analysis shows that the cash flow is negative in the first year, then positive and peaks in the later years. This indicated that financial trajectory of the project is strong. In summary, the project has an initial cost of 143.05 million euros and generates annual revenue of 17.37 million euros for electricity exports, with a growth rate of 2%. The project will reduce CO2 emissions by 105,314 tons per year, supporting environmental sustainability. Financially, the project has a pre-tax equity internal rate of return of 9.2%, and a net present value of 9.23 million euros. The project is expected to break even in 11 years and be cash flow positive and increasing over its 20-year life cycle, making it a sound investment.
So at the end, our conclusion to our project. You see at the left side the result of the modeling. For example, the annual wind speed calculated by the software is with 5.2 meter per second, very high. Or the capacity factor with 60.1% is also very high, because normally it's around 40%. And yeah, the annual electricity, which is exported to the grid, it's calculated with 400,000 426,663 megawatt per hour. And when you know that in New Zealand, the annual electricity consumption per inhabitant is 7.939 megawatt per hour, you can calculate that the wind power plant could supply electricity for over 50,000 people, and that is about 10% of the population in New Zealand. And at the beginning, we say that New Zealand has a goal that between 20 and 35% of the whole electricity is generated by wind power in the year 2035, and the wind power plant could help New Zealand to reach this goal. Yeah, but what speaks against the wind power plant? Obvious that the wind energy is depending on the wind condition, and when no wind is blowing, no energy is generating, and especially in the area of our wind power plant, the infrastructure is not so good. You see on the left picture there are small streets, and on the streets it's difficult to transport big materials of the power plant, like huge rotor blades or something else. Or new infrastructure must build, and that not only means streets but also transmission lines for the electricity power, and that causes extra costs. Yeah, but the location is in the near of the city, so it's reduced costs and losses because the distance is not so big. Also, the agriculture in the region plays an important role. You see it on the right picture. Farmers use the land for sheeps, and it could cause extra costs to buy this land from the farmer and to build their wind power plant. Yeah, but a positive thing at the end. In the near of Wellington is a wind power plant already in operation. So it's named Westwind, and it's located in Makara, which is west in the west of Wellington, and it's built between 2002 and 2009. So it's about 15 years in operation. It includes 62 wind turbines, and wind turbines can generate 142.6 megawatt per hour, which is enough for about 73,000 New Zealand towns. And that shows us that wind energy is already being successfully generated in the region around Wellington, and that is a positive sign for implementing our project. Yeah, and that was our presentation. Here are the references, and we say thank you for your interest and support of this project.